Welcome back. Today we're going to move on from talking about the operations of functions, the basic ones we know, addition, subtraction, multiplication, and division. Today we're going to dive into something deeper. We're going to talk about the composition of two functions. Now this is kind of exciting because it's one you haven't heard of before, you haven't seen before. A composition of functions is actually putting a function into another function, which actually can lead to some really cool, neat things. So, what I want to show you is two notations. So for composition of functions, they're always going to give you what the two functions are. So here, f of x is 3x plus 1. G of x is x squared plus 2. So you always have to know what functions you're dealing with. And then the notation for composition of functions looks like this. F, that little open circle G. That means composing function f with G. Now, a more standard notation, one that I think makes more sense to you, is to write it like this. Okay, so whenever you see that notation with the circle, I would always end up rewriting it. So it's g of 2 inside f of g. So it's f of g of 2. And the way that you want to do this, you always start in the inner function, calculate that, and then calculate the outer function. So what I mean by that is your inner function here is g of 2. Okay? So you want to start with that calculation. You want to calculate g of 2. So I use the g function, that x squared plus 2, and I put 2 into it. So there, 4 plus 2 gives me 6. Okay? Now, after you calculate that, after you figure out that g of 2 is 6, well, then you're going to plug that 6 into f. So you plug that answer that you got, now you plug it into the outer function because g of 2 is 6, so really what I'm looking for is f of 6, and I plug that in. So 3 times 6 plus 1, all I did was plugged the 6 into the f function. 18 plus 1 gives me 19. So what this ultimately equals is 19. So this idea of plugging a function into another function. So let's try it again. Now let's try it the reverse way. So this time, notice in this one, I haven't written the reverse order. So I, again, always want you to rewrite it looking like this. So g of f of 2, always rewrite it, and then you're going to start on the inside. So this time I'm starting by calculating f of 2. And f of 2, when I plug that in, I get 3 times 2 plus 1. So again, plugging it into the f function, 6 plus 1 gives me 7. Now that I have that 7, now that is what I plug in to my outer function. That's what I plug into my g. So now g of 7, 49 plus 2 gives me 51. Okay, so not only is this giving us practice with this idea, but it also points out something very interesting, that they are not the same thing. Okay, notice that reversing that order gives me a completely different answer. That's something that I really, really need you to understand, that the order matters. Okay? So let's get some more practice maneuvering this, okay? Because I know this can be relatively tricky. So let's try this. Now f of x is going to be the square root of x plus 3, and g of x is going to be x divided by 2. Again, whenever you see this notation, I would like you to rewrite it to look like this, okay? So f of g of 12, so I'm going to start on the inside. I'm going to calculate that inner function. G of 12, well, g is telling me x over 2, So that's going to give me 12 over 2, or that's going to end up giving me 6. Okay, so I have 6 now, and now I use that to calculate my outer function. I plug that 6 in to the outer function, to the f function. So square root of 9, my answer is ultimately 3. All right, so now let's calculate another one. G of f of 1. So again, whenever you see this notation, right away, please switch it to look like this. Write it in that notation, because then I think it makes more sense to you to see calculate that inner function. So calculate f of 1. So I plug 1 into my f function. Square root of 4 gives me 2. All right, I take that answer. Now that answer is what I plug in to the outer function. So g of 2, 2 over 2 gives me 1. So my answer here, when I compose those two functions, the answer is 1. All right, so that's what you do when you're evaluating for a number, okay? And this key concept really gets at that, okay? That explains it in a more mathematical way to read through. But ultimately, all you're doing is calculate the inside and then calculate the outside. All right, now, sometimes you're just going to be asked to compose two functions. All right, you're not going to be doing it just to evaluate. You're going to be simply composing those functions. So again, the best way is to do the inner function and then the outer function. So once again, I'm going to rewrite this. So this is going to be g of f of x. And now I'm actually going to show plugging the entire f function into the g function. Okay, so what that's going to look like, I'm going to take the whole f function, okay, that whole thing, and I'm going to plug it in wherever I see an x in the g function. That's what it's telling me to do. Put f into g. And this time I'm not going to be using numbers. I'm going to keep it strictly with variables. So that's going to look like plugging in that negative 2x plus 3. And then I still have the minus 2. I'm putting that negative 2x plus 3 wherever I see an x in the g function. And now, of course, I'm going to simplify. So 3 minus 2 leaves me a plus 1. And this is what I'm going to get after I clean up those like terms. All right, now this takes a lot of visualization, okay? This takes a while to get. So let's do numerous more examples to make sure you're feeling comfortable with this. So here, the first thing I'm going to do is I'm going to rewrite this. Okay, so you rewrite it so you can see I'm plugging g into the f function. All right, so I'm going to switch colors this time. So I'm putting g into f. So I'm going to look at g, and wherever there's an x in the f function, that's where I'm going to put it. So when I rewrite this, I'm rewriting f, but wherever I see an x, I put my g function. Okay, so again, this idea of putting a function into another function. So now I have to clear up the smoke. Now I have to simplify it. Well, to simplify it, I'm going to distribute that negative 2. And now combine my like terms. And this is what I get. So once again, another example of where the order definitely matters here. And so that's why I encourage you to rewrite it, because you're going to get different answers depending on which way you compose your functions. All right, let's move on to this example. So again, rewrite it. So this time I'm putting f into g. Okay, so I'm putting my f function here wherever I see an x in my g function, f into g. So that's going to give me, oh, I'm sorry, I wanted to make sure to use my colors. That 2x plus 1 squared minus 1. So I'm writing out my g function with f inside of it. Now, hopefully you can see that squared term. What's happening there is I'm going to end up having to FOIL that, okay? So don't forget foiling when you see it. Whenever you're squaring a binomial, that ultimately is going to lead to foiling. So that's going to give me 2x times 2x is 4x squared. 2x plus 2x is going to give me 4x. 1 times 1. Then I still have that minus 1 at the end. So I FOIL it out, still have the minus 1 at the end. 1 minus 1 cancels out. So you get 4x squared plus 4x as your answer when you compose it that way. Now let's come over here. And here I'm going to end up composing it the other direction. I'm going to put g into f. So I'm going to start with g, and I'm putting that in wherever I see an x in my f function. So I'm rewriting f, so 2 times, but whenever I hit an x, I'm writing my g function. All right, so time to clean this up, multiply those by 2, so I get 2x squared minus 2 plus 1, combine my like terms, and I get 2x squared minus 1. Again, completely different answers depending on the order in which I compose them. Let's look at a few more examples. Again, always rewrite it so you can see what's going on. So in this case, I'm putting f into g. So let's start with f. So I'm putting this whole function in wherever I see an x in my g function. So rewriting my g function with f wherever I see an x. All right, let's combine my like terms on top. So 3 minus 5 leaves me negative 2. And now 2x divided by 2 is x. Negative 2 divided by x is, or negative 2 divided by 2 is a negative 1. And so that's what I'm going to have left afterward. Now let's come over here and do it in the other direction. This time putting g into f and see what happens. So starting with g, putting that in to f wherever I see an x. So I start writing out f, but where I hit an x, so now I put my g in wherever I see that x. So here, 2 divided by 2 actually cancels right away. So from that, all I have left is that x minus 5 because the 2's actually cancel out. Now I combine my like terms, and I'm left with x minus 2. So throughout this process, what I just want you to remember is you're always putting a function into another function. And I can't emphasize enough that the order really matters in which you do this. So let's take a look at a word problem example, which kind of embeds two examples into one. So you have a coupon for $5 off of the price of any large pizza. You also get an additional 10% discount on any pizza if you show your student ID. How much more would you pay for a large pizza if the cashier applies the coupon first? So we want to find functions C and D to model the cost of the large pizza. All right, so let's have X be the original price. Okay, X is going to be the original price of the pizza. So now let's say the coupon. So if I apply the coupon to that price, well, the coupon is $5 off. So what I would do, I would take the price of the pizza and just subtract $5 from that. That's what $5 off means. Now, what about the discount? The discounted price of the pizza? Well, the discounted price is going to be 10% off. Okay? Well, 10% off means I'm going to be paying 90% of the cost. So I'm only going to have 0.9x left, because 10% off, again, all that means is I'm going to be paying 90% or 0.9. So now we're going to compose our functions. Compose the functions to apply the discount, then the coupon. So I'm going to apply the discount and then apply the coupon. So remember, that's what that means. You always work inside out. Apply the discount, then I'm going to apply the coupon. So if I'm putting d of x first and then the coupon, I'm putting d of x into c of x. So I'm just going to put that 0.9x wherever I see an x in the c function, ultimately giving me 0.9x minus 5. Now, what if I apply the coupon and then the discount? So I apply the coupon and then the coupon on top of that. So this time, I'm putting the x minus 5 wherever I see an x in the d function. I'm putting c into d. When I distribute that 0.9, I'm getting 0.9x minus 4.5. So how much more would you end up paying? Well, let's find the difference between these two functions. Okay, subtract these two functions. That cancels off. So it doesn't really matter how much the pizza cost in the beginning. All that matters is that it is a 50-cent difference. You're going to pay 50 cents more. Now, why is that? Well, because when you do it in that order, your coupon isn't applying to the discount. You're actually losing money off the $5, where if you apply the coupon first, you get 10% off the whole pizza, then minus a 5. Where if you minus a 5 first, you're losing money off of that $5. So that's why there's this difference here. And you can see that in the order in which you compose the functions, the order in which you apply those functions together. All right. So, after those examples, why don't you write a summary for me? Okay, take a moment, reflect on what we've talked about in this video, and then after you do that summary, just make sure you have everything written out, and then come back ready to do your practice work.